So from the given questions that we have, we are going to consider on our DC machines, which is working with the compound wound generators. If we are to consider the two typical questions that we are given, that is to focus on the compound generator. And also, if you check, this is still a compound wound generator. The only difference is that we are going to have two, which is a long shunt, and it can be a short shunt. That is what you're supposed to basically work with. So let's consider our first question. These are just questions that we're going to consider in our part of our revisions. On number 14, considering this, it's a 30 kilowatt, 300 volt long shunt compound wound generator. So if we're to consider, the first thing is the power that you're given, a 30 kilowatt. Remember I said this type of power is the power that is at the output. You're considering a generator. This is your output power, which is the electrical power that you'll be given there. With the terminal voltage, we have our terminal voltage. All right, so let's just have a sketch and try to also have the information that we are given there. So this is a long shunt. It is just similar to, remember, if you're working with the generator that is connected, that is a shunt. The part of, no, don't consider this to say long shunt, just to say a shunt generator. It's a parallel connection that you have. So the only thing that will be added to that parallel connection that you are used to is the resistance, is this series field that we are going to have now, which means on this case, we are going to have a series field which is connected to this armature. That is the major part that you're supposed to take note. You had this without this series field. It was not there. It was just like this, a normal shunt. But when it is considered now to be a long shunt, we are going to add the series field. Okay, so like I said before, this is a generator. We know on a generator, we are going to be supplying the current, which is different from a motor which takes in the current. So here we are going to be supplying the current from where? From the armature. So meaning to say we are going to have here the armature current. So we have got our resistance of the armature. This and that. This is our input, which is the mechanical. Current that is flowing here is the same current that is flowing in the series field. You're going to notice that it is the same current that is flowing from the series field. That current at this junction, another current is going to drop into this part of the shunt. Remember, that's your shunt field. And the rest of the current to the what? To the load. We are supplying the load. We are supplying the load. It's a generator. So as we are used to this, just for your basics to know, but we are used to this. You're supposed to know everything. So they said it's a 30 kilowatt, meaning to say you're given the power there, like I said, that is the output power. So in a typical exam, they're not going to actually specify this is the input power. No. They're just going to give you that. You know that is your output. And according to the generator, the output, remember, is our electrical power, where we have got our P out here and also the voltage, which is electrical. This is mechanical. All right. So let's move on. We're given also the terminal voltage V, which is 300 volts. And this, okay, it has a shunt field resistance of, so this is the resistance of the shunt here. We are given 175 ohms. So the resistance of the shunt is there. A series field, which is 0.1. We also given the series field, which is 0.1 ohms. That is what we are given there. And an armature resistance of, also given the resistance of the armature, 0.35 ohms. That is the resistance of the armature, 0.35 ohms. So the question is, calculate the magnitude of the generated EMF in the armature. The magnitude of the generated EMF in the armature. What is the magnitude of the generated EMF? This part of compound wound generators, this and that, it's just similar to what we had when we worked with the generated EMF. Remembering that the generated EMF can be taken, remember we're talking of a generator. So the generated EMF is equal to V plus the armature current times the resistance of the armature circuit. Considering that you are working with the armature circuit, what is it that is affected in the armature circuit? Which resistances are we having where the armature current is going to flow? It is going to flow in this path. What is affected there? We can see there is the resistance of the armature there. It is affected because the same current that is affecting even here, the series field is also affected. So we can tell that this resistance of the armature circuit is a combination of these two in series, considering what? The resistance of the armature and the series field. But in a consideration that the brush is also considered, remember there's that part of the brush conduct. If it is considered, you are also going to add the resistance of the brush. It's also part where the armature current is going to flow. So in this case, we are not told anything about the brush here. So meaning to say the resistance of the armature circuit, we are going to consider this part, the resistance of the armature and the series field, because we do not have this is just like a zero. We are not given. So when it is not given, we take it as a zero. That is the consideration there. What is representing the resistance of the armature circuit? It is all this. So we have the resistance of the armature, it is given. The series field, it is also given. That one of the brush is not given. We take it as a zero. So it's just like it's there, but as a zero if it is not given, if it is not stated. So what is that you want? V, we have it. The armature current, we do not have. So we are forced to calculate the armature current. Then we can find our generated EMF. That is what is there. You can see that V is there. So it's the armature current. And the armature current is the same as this part of the series field. Okay, remember guys, here that's where you have your E there. So in terms of the current, remember it's the same. So this is what I want you to be very, very careful about. So if we were given other currents, this current of the armature from our Kirchhoff's law, it is simply the addition of these two currents which are flowing away from the junction. This one is entering, and these two, they are flowing away from the junction. So they are going to add up to the armature current or the series field. Remember, I said armature current is the same as the series field. So instead of you using the series field, just use the armature current because it's the one that you have there on your formula. So it means the armature current is equal to the sum of these two from your Kirchhoff's shunt and that load current. So meaning to say, if we add the load current and the shunt current together, they will give us the armature current. But we do not have this. We also do not have this. Where can we obtain the load current? That is what you're not asking yourself. If I'm given the power output and the terminal voltage, The load current can be obtained. Remember, this is the electrical power here at the output. What is it that we have? We consider the terminal and the load current that is there. Remember, this is DC. So meaning to say, load current was going to be calculated from output power, from P out. Because we understand that P out is the voltage and load current, the terminal voltage. So simply divide by voltage both sides, you are going to obtain the load current, which is simply P out over V. And we have got the output power, 30 kilowatts, the voltage 300. So that's 30 times 10 to the exponent of 3 over 300. So that was going to give us the load current, which was going to be 100 amperes. So this is your load current here. So we now have the load current. What about the shunt? Let's consider where the shunt is. Across the shunt here, across this, there is nothing affecting except for that resistance only. We do not have any other resistor here. So meaning to say, as it is this voltage across here and this shunt resistance, they can give us the current, because talking of a parallel, there is no resistance within here. So this voltage that we are seeing is the same voltage that is across here, across the shunt as it is. So dividing voltage, the terminal voltage and the shunt is going to give us what? The current in that branch. That is the idea there. All right. So I shunt can be calculated. I can just even try to write it across here. So that is the shunt from the terminal voltage, the resistance across the shunt. So that is, we are going to obtain this. This is 300. And remember, the shunt here is 175. So that's 300 divided by 175, obtaining the shunt current of 1.714 amps. So with this current, together with the load current that we calculated, we are now going to obtain the armature current. So you see, it's not going to be a direct question where everything is given, the armature current. You just have to substitute. No. Some of these currents might not be given. And what is that you need to do is to calculate those currents using any suitable formula which connects that current. We talk of the load current, we talk of the shunt. Then together now, combine this, you're going to obtain the armature current. So that is 100 plus the shunt, which we calculated 1.714 amperes. So that is obtaining the current that is of the armature, knowing that the current of the armature is the same as the series field. Remember that. So that's 101.714 amps. And this current that we are talking about, this, it is the same here. Remember what I said? Armature current and the series field is the same. So instead of you writing the series field, because your formula it is referring to the armature current, that is why I had to calculate that as the armature current, but it's the same current in series. Remember, current is the same. So let's substitute our values. Now we have got everything. We can obtain the generated EMF. So V, we are given this V. Remember that was 300. So we are going to have 300 plus the armature current that we just calculated now. And our armature current is what? This is your armature current, 101. So you're going to take that as it is, 101.714 into the resistance of the armature circuit. And that resistance of the armature circuit is a combination of these. The resistance of the armature, which is 0.35, the resistance of the series field, which is 0.1, and the resistance for the brush, which we are not given. And if you're not given, you take that to be a 0. It's not there. Do not have anything about the brush contact. So meaning to say with this, you're going to calculate your generated EMF. So take note about this, the resistance of the armature circuit, where the armature current is flowing, every part that is affected by the armature current as it is like this. Not to say this, I know this is not armature current. This is where the armature current is flowing as it is. It is going to affect resistance here of the armature, the series field, because remember here, it is still that same current which is flowing here. It is still the same current. They are equal. So that is why the part of the series field is also affected, because that current is equal to the armature current. So it means it is the armature current which is flowing there. And also not forgetting the part of the brush, because sometimes they might give you that resistance, then you have to use it if you're given. But if you're not given, you take it to be a 0. You just equate that one to 0. All right. So this was going to give us 345. So that's 345,771 volts, just like that. All right. So questions can be like this, where you are being asked to determine, to calculate the generated EMF on a long shunt compound wound generator. So just like what we had, or that, just like this part of working with a long shunt, it can be on a short shunt. All right, so let's consider another question here and see how we're supposed to determine or to calculate whatever that we are given on this question 15. So these are some of the typical exam questions that you can actually find in your revision as you are working with your question papers. You see that there are some questions which are of this nature. You just have to try by all means to revise as much questions as you can, you know, your question papers. Just try to revise as much as you can. It's not to say when they say it's new syllabus, the questions has changed. No, questions are still the same. Only addition is to what has been added. That is where you're going to expect some other questions. But those topics that you had like this, nothing has changed. You just have to revise those old questions that you used to revise before. On number 15, they said a short shunt compound wound generator. So a short shunt this time is given this way. Let me just give you a sketch of a short shunt. So we are going to have from our terminals here. Right, sorry. So you're going to have the series. That part of the series is still there, or series field, still have it to the armature. All right. From the armature now, we are going to notice that the connection that is later on to be extended is in parallel to the armature only. Is in parallel to the armature only. We are going to have the shunt here, parallel to the armature only. So this is what we are going to have at the end. So you must be careful about this. Because as we do understand, okay, this is a generator, guys. Remember your input power. This is your PN. And also, you're going to talk about the armature current. Talking of armature current, okay, just consider here the resistance. Let me put it here so that you can actually understand me properly here. So let's say we have our armature current here. What is going to be the effect from your Kirchhoff's law? What is going to be the effect? The armature current is the one that is going to be flowing at the junction here. Another current is going this side of the series. Another current is going this side of the shunt. It has branched in two branches. It's no longer the same. Another one has gone this side. Another one has gone this side. So you have to consider your Kirchhoff's law. So on this part of the series field, we are going to have the current flowing, which is the series as it is. But that series, as you can see, guys, is the one that is going where? To the terminals. So this is also our load current at the end. And another current is going to flow in this branch of the shunt, meaning to say we are going to consider our shunt current affecting what? This part of the shunt. This is the shunt there. That is the whole idea that you just need. So your V and your power output. So the question here is, we just need to understand, guys, this concept. As we can see here from this, armature current supplies series and it supplies what? The shunt. But from this, we can actually say this armature current is equal to what? The sum, because it is the one that is supplying the series and it is also the one supplying the shunt. So it is the sum of the shunt and the series field. And if you consider the series field, what are you considering there? You're considering the load current also, because you can see that the series and the load, they're in the same branch. Nothing, there is no other resistance that is to be affected there. So the current here is the same current. There is no junction that another current is going to flow this side, another current flowing. No, there's no junction there. It is the same current. So these are some of the things that you're supposed to be actually good at. You're noticing this. Your diagrams, if you know your diagram, maybe somehow you've forgotten your formulas, but from the diagram itself, guys, it tells us a lot. The diagram itself. Let's talk of the voltages. Remember the previous case, we took the voltage at the terminal and we said it is the same as the one that is across the shunt. This time it is not like that, guys, because we can see that this voltage here, it is going to be the voltage drop. Let's say we have to consider here a voltage drop here as our V here. This terminal voltage is not the same as this one because there are two things to be considered here. There are two things that we have to consider. One, the voltage here of the series field, because here there's a voltage drop across the series field. So we must consider the voltage of what? The series field. And from this point where we were now talking of the parallel combination, where we're now talking of the shunt, there's its own voltage drop there. So you have to consider voltage drop here, V shunt. It's no longer the same as what we had before. Before it was just like this, guys. The shunt as it is then. So the voltage here, the terminal, is the same because there is no other resistance to be considered. It was only the result of the shunt that is there. But in this case, there is a drop here for this series field. There is a drop here for the what? For the shunt. So meaning to say, as you are to consider from those, your DC guys, electrical principles, this V is simply the sum of these two. Terminal voltage there will be the sum of what? The series field and the shunt. You're studying your diagram. All right. Anyways, guys, let's consider our question quickly. Because of time, let us just consider our question quickly. Let's take the information or the data that we are given. So they told us that it supplies a load with 65 amps. It supplies, the generator is supplying, which is true. So this is where we have our load current of 65 amps. So we are given the load current, which is 65 amps. Remember, the load current is same as the series field. So as we are given this, we also have the series field there. At a terminal voltage of what? Of 400 volts. At this point, we are given the terminal voltage, which is 400 volts. The series field, the series, shunt, armature resistances are these respectively. So in that order, we are given that of the series, which is 0,1, which is the first one. The next one is of the shunt. So we're also given the shunt 220 ohms. The armature resistance, we're also given that of the armature, which is 0.15 ohms. We're also given that. Calculate the brush contact voltage drop. This time they want the part of the brush to be included, and you're the one who's supposed to calculate it. Calculate the brush contact voltage. V brush is the one that we need. If the magnitude of the generated EMF is 420 volts, we are given the magnitude of the generated EMF, 420 volts. If this is given, what is going to be the brush contact? This is the one that we need. Brush contact voltage drop. Remember in the previous question that I talked about, I said we can calculate, or we can have our calculation of the, when we are considering any generated EMF, like any connection that you are given, you can consider any part that you have there. But in our calculations, we also have to consider where the armature current is going to flow. That is what we are going to consider now as the resistance of the armature circuit. All right, no problem. So you understand me in this explanation that I'm trying to say here, to say, in the previous case, you had to consider the armature current, the resistance that is affected there. But if you consider here, you're going to notice that this part is going to be also involved as we are to consider our generated EMF, because take a look where V is, this terminal voltage. The terminal voltage is affecting the part of the series field and the part of the shunt, which in together is a combination of these. So in calculating of your E, you're going to notice that this E, the generated EMF, was going to be calculated from this. All right, let's say you wanted to calculate that E because it's already given. Your formula was going to be V that we have. Remember, you're supposed to add. We are dealing with the generator add. So what are we going to add? We are going to consider that part of the armature, which is having armature current and the resistance of the armature. Also, we are going to consider or to have the part of the series field. So we have the current of the series field and that resistance of the series field in that case. So that is the part of what? The series field, the drop of the series field. And the voltage drop that was going to happen on the brush contact. On the brush contact. Remember the part of the brush. This drop here is the one that we are supposed to calculate on. Armature current times what? The resistance of the brush is the brush contact voltage drop. So I'm just going to write this as what? V brush. But we saw where it was actually taken from. As we just want to calculate the wall of that V brush as it is. So you'll see that the effect this time was here. The series field is considered on its own. It is not having the same current as that of the armature. No, on its own. So what is it that you have? What is it that you need to calculate? All right. So are we given this? We have got our E. Remember, this is what we need to calculate. The V is given. The armature current we do not have, but the resistance of the armature is there. The series field is there. What about the current of the series field? The current of the series field is given. Remember, the part of the series field is this one. So it is the same current flowing here, which is the load current. So we have this one. but we do not have that of the armature. Just like the previous case, let us try to calculate this so that we can have our V brush. Where are we going to have the armature current from? From this information, the armature current is equal to the shunt current plus that current of the series field. All right, that is what we had there. Armature current, remember, the shunt plus the series field I explained from the Kirchhoff's law. Where the shunt we do not have, this one we do not have. But the series we given, remember the series is our load. Remember that is our load current. So we have that one. So you're going to be forced to calculate this current of the shunt. From where? Let's consider what we have here. If, let's say, the voltage across the shunt is there, and the resistance across the shunt is also given, we can calculate the shunt current because it's simply that voltage over resistance. Remember your current consideration. Voltage over resistance. So it tells us that for the shunt current, we can obtain it from the terminal, from the voltage across the shunt, sorry, not the terminal this time. We don't consider the terminal. The shunt, this one, over its resistance, like that. Where we do not have this, but we have this. So the question is, where are we going to have this V shunt? From this formula that we stated from the terminal, we said V shunt is equal to what? The combination of these two. I mean, V terminal is equal to the combination of these two, the series and the shunt. So we can work from there and calculate V shunt, the one that we need here. All right, let's manipulate and make V shunt the subject there. So if we make V shunt the subject, it means we're going to take the series this side. Okay, so it is going to be V minus the series field. The V is there, but the series field is not given. We do not have that. We are not told about that. But we can calculate it because it is simply the product of these two, current and resistance. Remember, voltage, current times resistance. So if I have the current across the series field and the resistance of the series field, I have the voltage drop of what? The series field. That is what we simply says. So V shunt was going to be calculated from there. V minus the current across the series field, resistance across that series field. So what is our V? Terminal voltage, which is 400. Remember there we are given 400. So that was going to be 400 minus the series field. Remember, this one is the same as the load current. So wherever I see the series field, I see the load current. And what is our load current? 65 amps. So you're going to consider your load current there, 65 amps. Then the resistance of the series field, we are given, that was 0.1. So we're just going to consider, substitute this. That's 0.1. All right, so that was going to give us 393.5 volts, which is the voltage across the shunt field. With that voltage and the resistance of the shunt current can be calculated. So V shunt is given 393.5 over what? The shunt resistance, the resistance across the shunt, which is what? 220 ohms. So calculating this, you are going to obtain 1.789 amperes. Why are we calculating this? So that we determine the armature current, because we saw that was missing here. So the armature current now was going to be calculated. So meaning say the armature current, the shunt, we obtained our shunt as it is 1.789 plus the series field. Remember, your series field is the same as the load current as I explained before, guys. So that was going to give us 66.7 0.89 amps. So we have the current affecting the armature, which was missing here. We now have it. So you can calculate our V brush, guys. So you can even make it the subject of the formula, meaning to say E, we take V to this side, it will be a minus. So minus V, we take this voltage drop here to this other side is a plus. The moment you take it there, it will be what? A minus. We also take this series part to the other side, the series as it is, meaning to say we are going to remain with what? V brush. We have made that the subject of the formula. That is your V brush. So simply meaning to say that our V brush was going to be equal to what? What is the value of E? We have to substitute that 420. We are given that. So that was going to be 420 minus V, our terminal voltage. Remember that was 400. We are also given 400. So it is just a matter of substituting in this case. All right, so this was going to be 400. Then that is, okay, then that is 400 minus armature current times resistance of the armature circuit. All right, armature current, resistance of the armature circuit. Remember, our armature current is the one that we got that 66 here, the 66,789, and the resistance of the armature is there, 0,15. So this one, guys, is just a product. Substitute your values, the one that you calculated there. So that's the armature current. We calculated this. Remember, it was 66,789 times, you're going to multiply to the resistance of the armature, which is 0,15. Then subtract that part of the series field now. So the series field, we calculated this. The current across the series field is already given. Remember, the series is the same as the load. As you consider this part of the series, you say that is the same as the load, which is 65. And its resistance was given 0,1. So that's 65 multiplied to 0,1. All right, so that was going to give us the brush contact voltage drop. We are calculating, it's combined. Remember, it's supposed to be armature current times the resistance of the brush, but they want the voltage drop as it is. So inserting these values on your calculator, guys, you were going to obtain something like 3,482 volts as the voltage drop, the brush contact voltage drop. So let's do revise as much questions as we can. And also on the comment section, let's talk about areas that need to be perfected as we are revising for our exams, which are ahead of time. So let's do so. Revise as much questions as you can. Nothing has changed that much that you can be worried about. Do revise your previous exam questions. You see that it is still similar to what you're going to be also having in your final examinations. Till we meet again.